Welcome my dear students. Today we're gonna start a new lecture series on gravitation and gravity. So before jumping in straight to the Newton's law of gravity, it is necessary to know the historical background behind the invention of the general theory of gravity by Newton's. Before we get into this, let me tell you what are the topics that will be discussed in this series. You can see I have already written that I will cover the historical background that I have just told, and then it will be Kepler's law and universal law of gravitation, the gravitational constant, the acceleration due to gravity of Earth, and all these points from 1 to 10. Okay, in today's video we'll gonna cover mainly the first and the second topics. Okay, now let us just discuss the historical background. Okay, starting with Galileo. What are the contributions Galileo made? Actually, Galileo recognized the fact that all bodies are accelerated with a constant acceleration towards the Earth, irrespective of their masses. So according to Galileo, everything on the surface of Earth or above the surface of Earth is accelerated towards Earth irrespective of its mass. Okay, he also calculated the value of this acceleration, which we in later cases termed as the acceleration due to gravity. Okay, so Galileo also calculated the value of this acceleration, which was very close to the accepted value today, that is 9.8 meter per second square. Then comes Ptolemy. What was Ptolemy's contribution? Ptolemy, in his observation, which was actually regarding the motion of the planets and the stars, he was the first person to give a geocentric model of the planetary motion, which says the celestial objects, the stars, the sun and the planets all revolved around the Earth in a circular path. Although today we know the actual fact, but at the time of Ptolemy, to give such a geocentric model of celestial motion was kind of a good idea. Okay, then some 400 years later, one of the Indian great astronomers, Aryabhatta, he also proposed a model for planetary motion, and it was termed as a heliocentric model, in which Aryabhatta suggested that sun was at the center of the circle and the planets all move around the sun in this circular orbit. Then came Nicolaus Copernicus, Polish monk. He about 1000 years later gave an idea which was in contradiction to Ptolemy. What Copernicus said? He says the planets moves in a circles with the sun at the center. But since his idea, Copernicus' idea, was in contradiction to Ptolemy, the church that time prosecuted Nicolaus Copernicus for his beliefs. Then around 1546 to 1601, a Denmark data analyst, Tycho Brahe, he spent his entire life recording the observations of the planet with his naked eye. Later, his assistant Johannes Kepler interpreted his data and gave what is today called the Kepler's law of planetary motion. Okay, so basically Kepler's law of planetary motion gives three ideas, namely their first idea was regarding the orbits of the planet and is termed as the law of orbits. Then the second idea was regarding the aerial velocity and is termed as the law of area, and the third idea was regarding the time required for a complete revolution of the planet around the sun and is termed as the law of period. Okay, so let me first go to the first law, and that is the law of orbit. What does it say? It says all planets move in an elliptical orbit. All planets moves in an elliptical orbit with the sun situated at one of the foci of the ellipse. Okay, so before we discuss this in detail, I just want to give an idea about what is ellipse. So ellipse is nothing but it's a closed curve with two axes. One of the axis is this AP and the other axis is BC. The axis AP is termed as the major axis and the axis BC is termed as the minor axis, and these 2 points, fixed points on the major axis, this S prime and S, are called the foci of the ellipse. Now it is important to note that half of the major axis, that is, if I put a O here, half of the major axis AP, that is O, is termed as the semi major axis, and half of this minor axis BC, that is BO, half of the minor axis BC, that is BO, is termed as the semi minor axis. These two terms we will need later on. Okay, so this is all about the ellipse. Now we came back to the law of orbit. So what is the law of orbit? All planets move in an elliptical orbit. What is ellipse? We know already. With the sun situated at one of the foci of the ellipse. So suppose here is a planet, so it revolves with the sun. It revolves in an elliptical orbit with the sun at this foci, S. Okay. Now you can see, if we consider the sun at this foci, the orbit, the planet, when it comes at the point P, it is nearest to the sun, and when the planet is at the point A, it is farthest from the sun. This point, which is closest to the sun, is termed as the perihelion. Okay, it is termed as the perihelion, and the point A, which is farthest from the sun, is called the aphelion, right? Okay. Now let us now discuss the second law, the law of radius. What it says? It says the line that joins any planet to the sun sweeps equal area in equal interval of time. Okay, the line that joins any planet to the sun sweeps equal area in equal interval of time. So in short, we can say that the aerial velocity of the planet round the sun is a constant. Okay, the law of radius, what it says? The line that joins any planet to the sun sweeps equal areas in equal interval of time, that is, the aerial velocity of the planet around the sun is a constant. Aerial velocity of the planet round the sun is a constant. Round the sun is a constant. Okay. Now suppose in any moment this S is the sun and P is our planet. For any given time interval delta t, the planet moves from the point P to P prime. Okay. For this reason, it sweeps out an area, this shaded area. It sweeps out this shaded area, which is delta A. Okay. We need to prove that this aerial velocity of the planet round this sun in this elliptical orbit is a constant. Now we can easily do this by considering the central force system. Okay. Before going into this, let me just give an idea about central force. So what is a central force? Central force. What is central force? Central force is one for which the force acts along the line joining the object and the source of force. Okay, I repeat, a central force is one in which the force acts along the line joining the object and the source of force. Suppose here is a source of force, say be it our sun, and there is a planet that is moving around the sun. So this is our planet. This is our planet, and let the distance from the sun to the planet be r. So for this system to be central, the force must be a function of this position vector r. If such is the case, then this sun planet system is a central force system. Okay. So you understand what is central force. Central force is nothing but a force which depends upon the position vector r. Okay. Now here is the main idea. For a central force system, for a central force system, the angular momentum L is a constant. The angular momentum L is a constant. Okay, remember this. For a central force system, the angular momentum is a constant. So we understand that the sun planet system is a central force system, since the force acting on the planet due to the sun depends on the position vector r. Okay, very good. Let r be the position vector of the planet having mass m. So mass of the planet, suppose the mass of the planet be m. Okay, and r is nothing but the position vector of the planet. R is the position vector of the planet, right? So if the planet is moving with a velocity v, for a small interval of time delta t, the planet moves from the point P to P dash. Okay, and in doing so it sweeps out the area delta A. Okay, then what is delta A? Delta A equals half times r cross v into delta t. Actually r into time, velocity times some time equals some length. So this is dimensionally correct. This is area. Okay, and we said that v is the velocity of the planet, right? Then we can write the aerial velocity, then delta A by delta t equals what? R cross p by m. Why? Because here we put v is equals to linear momentum p by m. Okay, now we just simplify this thing, L by 2m. What is this L? I previously said that L is the angular momentum, is nothing but r cross p. Okay, so the cross product of the positional vector and the linear momentum of the object gives the angular momentum. Okay, so for this system, sun planet system, we get that the aerial velocity, delta A by delta t equals angular momentum upon twice m, and we previously said that for a central force system L is a constant. So we can write that aerial velocity delta A upon delta t equals constant. Why constant? Because we just calculated delta A by delta t equals L by 2m, and L being constant, so the right hand side become constant altogether. So this readily proves our second law of Kepler, that is the law of area, which just says that the planet sweeps out equal area in equal interval of time, that is the aerial velocity of the planet around the sun is a constant. Okay, now let us go to the third and the final law, which is the law of period. What does it say? It says the square of the time period of revolution of a planet is proportional to the cube of the semi-major axis of the ellipse traced out by it. Okay, so what is the period of revolution? The period of revolution is nothing but the time taken by this planet to make a complete return at this point. This is the period of revolution. Okay, this is the period of revolution. Now what is the semi major axis? I already said that this distance AO, this distance is the semi major axis. So what does this third law, that is the law of period, says? That if T is the period of revolution, T is the period of revolution of the planet around the sun, and if r is a semi-major axis, r is the semi-major axis of the ellipse that it traces out around the sun, then by this law we can write that t square is proportional to r cube. Okay, so the square of the period of revolution is proportional to the cube of the semi-major axis of the ellipse. We will prove this relation later on when we discuss Newton's universal law of gravitation. Okay, so in today's video we discuss in detail the Kepler's law of planetary motion, that is the law of orbits, the law of areas, and the law of period. Okay, so that's it for today. Do like this video and do subscribe to my channel.